Hello, everyone, and welcome. Thank you for joining me today. We are going to see how to use dependency injection to write maintainable software. I'm Francesco Zoffoli. I'm a software engineer building monitoring system at Meta. I'm passionate about C++, and I use it throughout my career. I'm the author of the book C++ Fundamentals, and in general, I like to write and talking about C++. Before we start, some mandatory disclaimers. Getting hard data about what I'm going to talk about, it's very hard. And so there's going to be a part that's driven by experience or what is commonly used in the industry, but it's hardly a hard rule. And we are going to see a bunch of tools, techniques, suggestions that you need to follow, you can follow, but the context is always relevant. And you need to make the decision for what is the right choice to make in your context. So today we are going to talk about dependency injection with a brief introduction. We are going to see what are the kind of dependencies that we can have. We're going to look at how we can pass these dependencies, and finally, how we can abstract components. But who heard about dependency injection before? Raise your hands. So almost everyone. And who's doing it consistently throughout their code base? All right, I was expecting more. Hopefully this is going to help all of you to use dependency injection in an easier way. So your software is probably composed by multiple components, and these components interact with each other. And when they interact, every component is going to have some observable behavior. An observable behavior is everything you can observe out of this component. Let's say a component has an add function, and this add function, it prints to standard out. This is an observable behavior, but very likely this is not the contract the component promises that when you add something is going to print. So a subset of the observable behavior is going to be the intended interface. And the intended interface is the contract that is specified. And with contract or interface, when I'm going to be talking about this, I mean the set of precondition and postcondition of this interface. And then there's going to be the usage that, if you're lucky, is going to be a subset of the intended interface. And this is key to understand dependency injection, because when we write a component, and here basically the shape specifies the interface. So we have a user which exposes some interface on the left and then uses some interface on the right. And since the user is only programming against the interface, it doesn't matter which one of the implementations it receives, and it shouldn't matter because it should program only against the interface. So considering that the user doesn't care about which one of the implementation it should use, we should specify which one. And this is the point of dependency injection. We want to inject the implementation. We have some implementations which implement an interface. We have users which expect interfaces. And then we have a higher level code which is deciding which implementation to pass to the user. And the key part about the dependency injection is that you don't want to instantiate your own dependencies. Why that? Because if you're instantiating your dependency, you know the concrete type of the object that you're using. And this means that you're not programming against the interface anymore, but you know the concrete type. And it's also harder to change the types you want to use throughout your system. So instead, the dependencies should be passed as parameters. And if we do that, we are going to end up with a system which looks like this, where the blue components are our implementations, and they either implement or use some interfaces. And then there's going to be a main component or a higher level component which instantiates our concrete classes and does all the wiring, passing the concrete implementation to the various components as they expect. And if we are doing this properly, we are going to see that we can reason about our system locally. And what I mean is this is that, let's say we want to inspect component B. Component B implements an interface and uses some interfaces for its logic. And the contract of these interfaces is very well specified. So it means that you can look at the code of B, at the calls it does to the interfaces it depends on, and verify whether these satisfy the interface. You don't have to have a global view of the system. And this also allows you to mock the interfaces and do easy testing. So we've been talking a lot about dependencies, but how you pass dependencies around is actually important. And the reason is that when you're defining the dependencies, you're imposing constraints. And the constraints are imposed on the user and on the implementer. What do I mean with this? When you're implementing, let's see an example. For example, in foo, we are taking the dependency as a shared pointer. This is imposing a constraint on the caller of foo, because we are specifying the lifetime memory management for our dependency. But this gives more freedom to the implementation, because with the shared pointer, we have additional functionality that we can leverage. For example, we can take a weak pointer. On the other side, when we have bar, we just get the reference. So there's no constraint on the user, because everyone can give you a reference on an object. But then in the implementation, we have a more restricted set of functionalities, because, for example, we cannot store or we cannot pass it to an API which requires a shared pointer. So a dependency should impose all the required constraints for its functionality and no more, because someone is paying for that cost. And one of these parts is actually that we don't want to force the lifetime management for the dependencies. And the reason is that some component is going to be, something is owning our component and is responsible for the lifetime of our component. And that same thing can also be responsible for the dependencies of our component. Our component is just saying, I need someone to do something for me. It's not its responsibility to know when this thing is created, when it's destroyed, where it's living, where it comes from. It just wants to delegate this work. And this means that we are going to take dependencies as references, and especially we are going to avoid smart pointers. But let's look a bit at the options we have for taking dependencies. And for this, we are going to see what are the types, the various types of dependencies. And we have two different types of dependencies. One is data, and this is when you depend on some information. And the other one is behaviors, and that's when you depend on some action. Let's look at data. So data must always be read-only. And the reason for this is that you want to avoid action as a distance. What is action at a distance? Here we have two components, component 1 and component 2, which are accessing the same shared variable. Here I'm taking the same global, but it doesn't have to be global. It can be the same variable referenced by both. If component 2 is writing into this variable, and component 1 is reading into this variable, they now are coupled because component 1 can see the behavior of component 2. And when we are working with dependencies, we want to have our dependencies explicit, otherwise there's no way to verify their behavior. The other aspect about data, when you're taking dependencies on information, is that this information can be constant or might change over time. And this is a constraint we are imposing on the interface. Because if we want to take data which changes over time, our implementation will have to deal with this data which can change. So it is more complex, but we are giving more freedom to the caller. And also talking about data, what is the interface for this information? And the interface for this information is the shape of the data. So in these cases, you want to use value types, and you want to prefer making the type explicit, using structured type. So for example, using a struct with named field or a schematized type. What I mean with here is like protocol buffers, thrift, cap and proto, anything where you can define a schema and then there's gonna be types generated to represent that schema. The important thing is that looking at the type, your user needs to understand as a user what data it needs to put there. And as the implementation, what data I can get there. So especially try to avoid using JSONs or maps of strings to variants or anything which is extremely dynamic and you cannot have guarantees about what is inside. Talking about the shape of the data being the interface, there is a common theme. And we can see that the most generic solution tends to have the highest cost in performance. So let's say, for example, that we want to pass a sequence of data to our component. So we have a dependency on a sequence of data. We could take this as a vector, so using the concrete type, and this is going to have the maximum performance, but it's the least freedom to the caller. Because if I have a vector, I can only pass a vector, right? So a vector works with vector, but if I have an array, I will have to convert it to a vector first. And if I have a set, same thing. The other alternative is to use a view object. For example, an std span. These are going to have performances similar to the vector, but with more freedom for the caller. For example, it works with the vector, but also works with array. It works with any contiguous data structure. But again, doesn't work with the set. The other option is to use a polymorphic object. For example, any range, which is in the ranges library or in Boost. In this case, we are paying a cost with performance because this type is type erased, but it gives the maximum freedom to the caller because this works with anything which is a sequence of single data. The other option is also to take a template parameter, if you can do static polymorphism, and you're gonna win maximum performance and maximum freedom, but of course there are other trade-offs in that choice. Something to keep in mind when you're looking at these options is how they compose. So for example, if I want to pass a sequence of sequences of integers, and our user might have a vector of vectors, if I take the type as a concrete type, this is gonna work, no problem. If I take it as an any range of any range, this also works and it's not a problem. But if I take it as a span of span, I have a problem. A vector of vector is not compatible with a span of span. So I'm forcing the user to convert again. So we need to evaluate the correct choice to make depending on the use cases. If we had a single dimension, you might use a span, but if not, it could be just more convenient to use a vector with the same cost for the user. So we said the data can be constant. How do we handle the case in which we want to support some data which is not changing? We can take it as a const reference. If you were here for my lightning talk, I wish we had an immutable reference to make it clear to the caller that this cannot be changed, but at the moment, I haven't found a solution for that. And the important thing is data must not be changed for the duration of the component. And this is because it's actually very surprising when you're implementing something and your const ref changes while your function executes. And the other aspect is that it's undefined behavior if it's done by a different thread. So you will need some kind of loop to end up modifying your variables, which is going to be quite confusing anyway. The use cases for data which is constant is normally to hardcode parameters. So you have a function, in your implementation, you're taking a timeout, and then you just want to hardcode this timeout. The other option is for parameters which are not changing for the duration of the program. For example, CLI flags or configurations that you're loading at start time. And this is the most preferred way of passing data because it's also the simplest. Looking at data which might change, the data is still read-only. Someone else might change it, but we cannot because we want to still enforce the independence of components. So if your data can change, normally it's the contract that you're offering saying, I support data that change. It makes sense to offer it to change it from multiple threads. And the reason is what I said before, that if it's just a weird loop if you're doing in your own thread. And to do that, you want to make it clear. So you can use an atomic ref. These has some requirements of the type that you can use in the atomic ref, and also copies at each axis. The other option is to use a fully synchronized. A fully synchronized is a data class which puts together a mutex and the payload. And it ensures that you're locking the mutex every time you're accessing your data. This has the drawback of risking contention. How can this happen? Imagine that you have two components, component A and component B, both accessing the same synchronized. Component A accesses a read lock, because we can only get a read lock out of a const synchronized, and holds it for a very long time. In the meantime, your producer wants to update the data that we have into the synchronized. And after that, the component B tries to get a read lock. Depending on your implementation, this read could be blocked or could go through seeing the old data, but in any case, the fact that component 1 existed prevented component 2 from seeing the most updated value. So this is one of the drawbacks of synchronized and using shared logs. The other option is, I'm not sure what happened. All right. The other option is to use a Folly observer. The Folly observer is a data structure which holds various versions of the data. So when someone asks the data from the observer, is going to get a snapshot. At the same time, a consumer can push a new version of this data, and the initial snapshot is left unchanged. The next user which is going to ask the data is going to get a new snapshot, the most up-to-date, and the two snapshots can live together. When the first component is going to be done with the snapshot, this data is going to be free. So this decouples the contention between the two components, because now the behavior of component 2 is the same whether component 1 exists or not, but you're paying a cost for this. The advantages of using this approach instead of a more common approach, which might be using a function to fetch this data every time you need it, is that it's super trivial to do the test. Because you're just passing data or references to data, in your test you can simply pass the wrapper, set the value directly, and it's going to be easy to test the behavior. The other aspect is that it's very easy to change the producer of the data. Your components are just accessing references to this data structure which are mutable, and whether this comes from a thread or whatever else that's running in the background or something that's triggered by the user, they don't care, and they're not going to find out. So it's a nice decoupling between the components. The use cases for this is pushing data to the component. This can be useful for hot reloading. So for example, if you have configuration changes which are regularly reloading from disk, or if you want to expose data which comes from a source but the freshness is not critical. For pool, a behavior is often the best solution. So what is a behavior? A behavior is a stateful action. So for example, sending a request to a service or scheduling some work for happening, or can be also getting data on demand, like reading a file from disk or fetching some data from a database. Or it could be a pure computation. Imagine you have a component which needs to compute the price for something, and this price calculation is very complicated, but it's not the responsibility of the component. So the calculation of the price can be a dependency, and this dependency will be a behavior. So the behaviors could be single actions or bundles of actions. In the case you want to support runtime polymorphism for a single action, you can use an std function or an std function ref. And this is how you will be using it. You define your dependency, in this case a configuration loader, which takes a config path and returns a config. And in your function, do stuff, you just take your config loader as an argument. And then when you call your function, you can use a lambda or you can use any single function to perform that. If instead you want to support compile time polymorphism, what you can use is a concept and leveraging std invocable and invoke result. You would define a concept which checks that your type can be called with a config path and checking that the result of calling your object with a config path is going to give you a config. I'm not going to go into how to define the concepts because there's been already an amazing talk about that in the conference. When you want to use the concept, you can define a template. In this case, you can see I'm using auto in the function, and you can constrain it with the concept. And then we call it in the same way in which we will call the runtime polymorphic one. A bundle is a collection of actions that go together. In case we want to do runtime polymorphism, we would want to use an abstract base class. Here we just define a virtual destructor and a set of virtual pure functions. When you're following this pattern, you really want to avoid putting implementation into your abstract base class. The reason is that anything that you put in the constructor, any data members, and all the constructor of these data members recursively are going to be executed every time you instantiate anything that derives from this class. So for example, if you have a mock, and this mock is going to derive from this class, you're going to have the constructor and the data members executing all the time. If you have any kind of side effect in your constructor, you're going to pay for this side effect in your tests or anytime you want to instantiate it. So just avoid it. Make a super simple class which has only pure abstract methods and derive from that. In the case of static polymorphism, the solution is, again, concepts. So you can define a concept which asserts that the type you're providing as the expected signature. And you can then take this as a parameter similar to what I showed for the single bundle as a template. The nice thing about this is when you want to mock either the runtime polymorphism or the static polymorphism, the approach is identical. In this case, I'm using a Google Mock to create a mock. And you can simply use your mock functionality to create functions which are not inheriting from anything. So the only difference you would see between using the runtime polymorphism or the compile time polymorphism is that the mock sender will derive from iSender or not. But this is very nice because you can reuse the framework. You don't have to learn something different for this. So in summary, in a behavior, we want to use for single action, runtime polymorphism, std function or std function ref, single action, static polymorphism, concepts. For a bundle, runtime polymorphism, abstract base class. For a bundle and static polymorphism, a concept. Let's talk now how we can pass the dependencies. So we can pass the dependencies to our component in two ways, from the constructor or as an argument to the function. The important thing is that we want to avoid setters. They enable cycle, they confuse lifetime, they force to handle the case in which the dependency is not set, and they force you to handle the case in which the dependency is set in the middle of your computation. I highly doubt that who uses setters is defending from that. So let's see an example. You have component A and component B, and you set the dependency on A to B. But imagine that now in the destructor, A accesses B. This is a dangling reference. And then you can have B that sets the dependency on A, and now you have a cycle. This is going to be very complicated to change later on. Let's look at an example of how you can find classes in the wild. You would have a foo which needs a logger, and it takes a logging path as a argument. And then in its constructor, it creates a file storage with the path on where the log is going to be stored. And then it creates a structured logger and then assign it to the logger. And then it's going to use its structure logger for the duration of its lifetime. This is problematic because the foo class needs to know about the structure logger, which is an implementation of iLogger. It needs to know that the dependency of structure logger is file storage. And it also needs to take the logging path and pass it to the file storage, while this might be completely irrelevant to the goal, the responsibility of foo. So we want to avoid to do something like that. A positive thing about this, though, is that it's actually very easy to use because you just instantiate it with the path that you want to pass. An alternative, if you were instead doing dependency injection, is that your class foo just needs a logger, and it wants to outsource the problem of what is this logger doing. So you just take a reference, you store it internally, and then you use it throughout the lifetime of the class. This makes it a bit more complex to use foo, though, because now the code which instantiates foo also needs to know about the structure logger and the file storage. But this has a few advantages. And one is the decoupling. As we were saying, foo doesn't need to know anything about the concrete implementation of logger. And also, you can change file storage. For example, it might take, we might change the type of the path from string to a path. And foo doesn't have to change because it doesn't go through its constructor. Lifetime is automatic because everything is on the stack. It's the same in the first example. Everything was a unique pointer, but this is going to work only as long as everything takes the dependencies as a unique pointer and everything is managing the lifetime of their own dependency. And the other big advantage is that you can easily share the logger across multiple classes. But what I present is a bit of a straw man, right? I talked about not injecting dependency at all and getting them as a reference. There's also the option of using a unique pointer. And this is something you might be seeing in your code. Most of the advantages are the same as using the reference, except for the sharing part. And that's what I mean. And the example of sharing, you can see also in the testing. In this case, again, I'm using Google Test, and I'm creating a fixture which is setting up the data for our test. And there's a class, which is the concrete class, which is under test, which takes a mock dependency. And we are passing it as a unique pointer. Now, in the body of our test, we want to set the expectations on this dependency, but we don't have the dependency anymore. There are solutions to this problem. You can lick the pointer, but they are quite hackish. The other question is, why not using the shared pointer? And the shared pointer works. If you consistently use shared pointer everywhere in your system, it always takes by shared pointer, it works, but it's not necessary. And you're forcing the lifetime management of the dependencies on everything in your system. My point is that references are universal. If you have an object, you have a reference to the object, and they always work. The thing to be careful in the constructor, but in general when using dependency injection, is to be careful about piping. Is what we saw initially with foo. This is when you get some data, and the only purpose of you getting this data is to pass it to someone else, and you're not using it directly. So an example here, we have a config loader which takes an action which takes a config loader and the path, and the only thing it cares about is getting the configuration. A way to avoid the piping of the data is to actually change my action to take a function which takes no argument and just return the configuration, and then bind the path to the loader at the higher level when we are passing this dependency. Of course, in this case, we could have passed also the configuration directly, and you should have preferred that if it was possible, but this is just an example to show the issue. The other option for passing arguments is, or dependencies is through function arguments. The use cases for this is when you use functions. Dependency injection does not mean that you need to have everything in classes. C++ supports functions. Functions are amazing. Use them liberally. You don't have to have everything as classes. to use dependency injection. And the other case in which you might need to pass in this way is when the caller needs to control which instance of the dependency to pass to the component. So this dependency might be changing every time you're calling it. Or alternatively, if the lifetime of these dependencies is shorter than your component. If you're passing to the constructor, there's the expectation that this dependency is going to be alive as long as the class is alive. And if this is not possible, you can pass it as an argument to the function. So let's see an example for this. Let's say we want to format a message for a user supporting internationalization. We could have an interface, which is our translator, which takes an untranslated message and returns a translated message. And then we could have a formatter, and this formatter takes the translator to use to translate the message, and it returns the formatted message. In the picture, we can see a stack, right? When the bottom part is the part which happens earlier, and at the top is the part which happens more recently. So initially, we create the formatter. And then we start processing data for the user. When we get this, we start this processing for the user, we can start to find out what is the language for the specific user. And once we have the language, we can instantiate the translator for the appropriate language, and then we can code format. But this is not the only option we have. We have another option. And the other option will be for the translator to take the untranslated message and the language, and then the formatter takes the translator as a constructor parameter, which can use for the duration of the program, of the component, and then format takes the language. Do you see a problem with this? It can be a function, but it's also doing piping. The formatting is getting the language, and it's piping it to the translator, but clearly before we didn't need it. So how can we break this loop in these situations? And the advantage of this solution is that first, we are instantiating the translator and then the formatter before processing the user. See, the order is inverted. Now we have the translator and then the formatter, while before we had first the formatter and then the translator. Right? We inverted the order in which you can create the instances. But we said that we wouldn't want to do piping. So the other option is to use, again, a translator which takes an untranslated message and give us back a translated message, and taking the constructor. How is this possible? We said we need to know the language of the user to be able to instantiate the translator. And this is because we can start instantiating the translator and the formatter after we started processing the user. So what I want to show with this is that by passing dependencies in the constructor or in the function, you can specify, you can get to system where the place where you're creating your objects, so your dependencies, changes. And it's up to you to choose the solution that works for your case. I don't know how expensive it is to create your translator, or whether the formatter has some specific data that you cannot get access only after you start processing the user. But the other thing is that here, for example, we start processing the user, and then we are talking about instantiating the translator. But we were saying that as part of dependency injection, if we are instantiating the objects that we use, we need the concrete type, and now we are locked into using the specific object. And that's bad. And we can solve this with factories. So a factory is simply it constructs a dependency from some parameters. But a factory is just a dependency. Everything we saw so far about passing the constructor, passing as a function, passing as a reference, it still applies to the dependencies. So when we are creating the dependency, we need to define the return type. And this return type needs to be abstract because we want to program against the interface. So we cannot return the concrete type So which type can we return? Well, I lied. In the case of static polymorphism, you can return the concrete type. With the concept, you can check that the result of calling your function satisfies another concept. In this case, config-like is a concept. And when you use this config loader, which satisfies the config loader concept, you can assign it to auto, so you're not going to specify the concrete type. You're just going to specify that it satisfies a contract. But the config loader is going to return by value a concrete type. But this doesn't work when we are talking about runtime polymorphism. So what can we return? A unique pointer is an option. For example, we can instantiate our concrete class and return it as an interface. And it still works when our foo depends on an iBar, and we have iBar already in our scope. We just capture it and we pass it on. But how does it work if instead we have an iBar factory? And I hope that right now you have like your bell ringing and saying, what are we looking? This is over-engineering. You will never get to a system which looks like that. But actually, it's not that rare. Let me show you an example. Let's say you have a factory which returns a file reader. And this, as a concrete implementation, you want to return a buffer, the file reader, which needs a buffer. And you don't want to create your own buffer. You have an allocator providing the memory which backs this buffer. Now your allocator is a factory, and your buff file reader needs the return of this factory. It's not super common, but it's also not super rare. So the problem here is that the buffer factory gives us a unique pointer to the buffer. And then, since buff file reader takes everything as reference, we are dereferencing, but now we have a dangling reference. How can we fix that? Another option is to use a shared pointer. The function takes a shared pointer, a function returns a shared pointer, and again, we get our shared pointer from our factory with the reference, and we are still in the dangling reference. So it looks like we didn't improve the situation much here. But the shared pointer actually has a nice feature, which is the aliasing constructor. So what we can do here? Here, in the body of the function, we create a holder. This holder is a struct which is responsible for the lifetime of our component and all its dependencies. You can see that here we have foo, which is not a shared pointer, it's just by value, and the shared pointer of iBar, which is returned by our factory. We then create a shared pointer with the holder, and using the aliasing constructor of the shared pointer, we tell to this new pointer, you're responsible for the lifetime of the holder, but when you're dereferenced, you point to a sub-object of the holder. So the shared pointer, which is going to be returned, is going to be responsible for the lifetime of everything, although from the point of view of the consumer, there's not going to be a difference of whether the shared pointer owns just our foo or the foo and all of its dependencies. The advantage of using the shared pointer is that it's familiar to most programmers in C++. It's available, and it interoperates well, because many libraries are giving you dependencies as shared pointers or expect dependencies as shared pointers. The disadvantages is that it has a needed feature. We don't need the shared ownership in this case. We just need the aliasing constructor. And there's also the risk of dangling references. Let me explain why. In the case of our factory, sorry. Yeah, I think there's a mistake in the order of the slide. So when we want to use the shared pointer, the only pattern that we want to follow is to get the shared pointer and then the references into the reference, and forget the shared pointer exists. And the reason is because if we structure our code like in this example, when we have a foo as a local variable a, and we are calling bar, which has a dependency on this interface. And then in bar, we create a factory, and we capture A in the factory, and we call bus. And in bus, we call the factory to get our B. If now we take this shared pointer, and we store it, for example, in a vector for later processing, or we spawn a thread without ever joining on the thread, and we return from the function, we have no guarantee that we are not referring to any of the variables which are in the stack above. And that's why I'm saying, if you follow this pattern, you're going to be good. And in general, this is the same concept about structured programming and structured concurrency that you might have heard already mentioned in this talk. And if you're not familiar, I highly recommend checking out, because it really helps in making your code correct. The other alternative to the shared pointer is using an older pointer. So an older pointer is basically a subset of the shared pointer, which only exposes the feature that you need, potentially as the copy and move constructor deleted so that you cannot move it around. Personally, I don't have production experience with this approach, but I think it's something that it's worth taking a look at. The other aspect with factories is that they are just functions. So testing, again, it's easy. We can create a mock function for our factory and pass it to our class. When we go in the testing, we can create the instance of our mock dependency, set the expectations on this dependency, and then configure our factory to return the dependency. If we need to check if our factory is going to be called in the constructor of our class, so here, we cannot use the fixture. We need to instantiate the class inside our test. So we talked a lot about how to pass the dependencies and all about how the lifetime is managed by the owning component. But what we get with this is that we're going to end up with a main which has 10,000 lines. It needs to wire all of these components, and the user doesn't want to do all this work, but also doesn't necessarily know about what is the correct wiring to get the behavior that they want. So how can we solve this? We need to expose a component which abstracts over all the sub-components. And this is how it could look like. In the picture, the round thing is an interface which is provided, and the half-moon thing is a dependency which is expected. And we can expose a component which has a clear interface and a clear dependency and hides internally all of the small components which allow it to expose the behavior that it needs. How can we do this? We just saw with factories how we can create a function which gives us back a component which is responsible for the lifetime of many dependencies. But the other option in this case is to use a struct. How does it look like? We have a function which returns by auto and takes as parameters all the dependencies of our macro component, always by reference. Then, inside the class, we define a struct, and we return this struct passing the dependencies to it. The implementation of the struct is going to have in the private field all the components that are necessary and are part of our subcomponent. The constructor is going to do all the wiring for this subcomponent correctly. And then, in the public part, we can expose the part which provides the interface that we want to offer. The other alternative here could be, for example, to have A in the private section and expose only an interface reference to A. That will give us more flexibility, but I argue that in this situation, we are not talking about, like in a factory, polymorphism or being able to change which component we return. You can see it as an alternative to a more complicated constructor. So I think there's no problem here in exposing the concrete type. This is possible because there's return value optimization and there's copy elision. So when the function is called, it doesn't impose a requirement on all these objects to be copyable or movable. Alternatively, the other advantage of this approach is that we can expose multiple interfaces. Anything that you want to expose, you can just put in the public section, and you're going to have multiple interfaces for this. The other advantage is the lifetime, again, is automatic. If this struct goes in the stack, everything is going to be destructed correctly. If it goes as part of another dependency, maybe as part of a factory, it's still going to be all automatic. You don't have to worry about allocations, pointers, lifetimes. The disadvantage is that there's no polymorphism, but in the case we want polymorphism, we can always use the factory pattern, which is basically identical. And the other big disadvantage is the physical dependency that you impose. So basically, whoever calls your make function is going to have to include all the headers of the concrete components that that are part of your macro component. So this might be a reason to prefer the factory, because you can split this away. But this is a trade-off that depends on your case. Another great advantage of this approach is actually testability. Imagine you have a component which has a clear responsibility, but a part of its logic internally, it's very complicated, and you would love to be able to test that in isolation. What you can do is splitting the logic of this component into an implementation detail. Then you can test this implementation detail in isolation, and then you can expose a macro component that is hiding the fact that there's this detailed internal split of logic. And from the point of view of your user, this is going to look identical to the case in which you don't have this split. So it helps with testability as well. So the advantage of the abstracting the component is that it enables to compose higher level components, and it provides facilities for testing. In conclusion, we saw an overview of what dependency injection is, how to define the interfaces for data, informations, and behaviors, actions. We saw how to pass the dependencies to our components, either through a constructor or as a function argument. And we saw how we can defer the instantiation decision about the concrete types through factories. And finally, how you can take all of these and apply it recursively to create bigger and bigger abstraction so that your software can be always at the correct level of abstraction, merging components which make sense for what you're building. All of these that I showed to you are tools. They are to manage complexity and help you create code which is easier to evolve. But there's a trade-off between flexibility, understandability, what you are introducing into your code base. So with this, I hope that you're going to be able to start applying dependency injection and make your code easier to maintain in the future. Thank you. And if you want to ask questions, you're more than welcome.
I'm going to be the one that asks it. But how about using SharePointer everywhere? What are the pros and cons of that? Why would you recommend using references over SharePointer? Assuming, for example, these are just a few components here and there, and the performance overhead of actually instancing the SharePointer is not that big, isn't it simpler to use a SharePointer? Does it avoid more mistakes like with lifetime stuff? So I want to hear your thoughts on that.
So I think the main trade-off, so first, can it work? Yes, it can work. There's no fundamental problem for which it cannot work. You're using, continuing from your talk, a more powerful tool than what it's needed. So there is an advantage with the SharePointer that the problem with lifetime I was mentioning, it's harder to achieve, but you risk more going into cycles in the dependency graph. But the other aspect is that if your code requires the share pointers to be correct, likely you're not following the structure programming and structure concurrency principle, which helps not only with the lifetime of your code, but also with reasoning about what your code does. So for simple cases, like in some situation where maybe the concepts of lifetime and dangling reference are not that well understood or clear, probably the share pointer can be a safer choice. But in general, I think it's adding more complexity to something that it's not needed. But I think it's a perfectly valid. Like if everyone consistently uses a share pointer everywhere, it works.
Another question about the wiring up logic, the macro components and that. I mean, wouldn't it be better to use a library for that, like Boost DI and things like that, to just simplify it and let the compiler take care of it?
Yeah, I'm gonna take on what you said, like simplify it. So I take, first, most of this is derived from experience I had with various systems where I saw this working. And I personally never saw professionally a system using dependency injection library. I think this might be more common in other languages. I knew about Boost dependency injection for a while. I took a look a few times, but then in the concrete aspect of things, I never saw it used. And the other aspect is that, at least from what I saw from the documentation, it feels like it's adding more complexity than simplicity. Here we are passing references around. And in general, you're gonna have, 3, 4, 5, 6 dependencies. And if you're creating these macro components, you're never gonna have many more than that. So I think dependency, like the Boost dependency injection is very powerful from what I saw. It can support a lot of cases. It's just that I never saw it used in production. So I don't have a concrete opinion on how it's used, but I also never felt that it was solving a problem I had in my code base.
When you create a type that takes in the dependency and then later uses that dependency, if you're only using that in that one place, you're exposing a longer or a requirement on a longer lifetime to your user than what you actually need. Would you recommend in all of those cases to inject as parameters in the minimal place where you have to use it?
So the question, I think, is when we are passing as a parameter as a constructor, we require the lifetime of this dependency to be longer than the object that we are creating. And instead, if we add it as in the function, that can be shorter. The thing to keep in mind is that when you're passing in the constructor, you're going to call the constructor once, maybe, but the function might be called multiple times. And when you pass it as a function, so you have the overhead, programming-wise, that you need to pass this argument every time. So it can be a bit inconvenient, although it happens. For example, in a class which is accessing the database, normally in what I've been doing is that you take a connection interface as a parameter. And the reason is that when you retry, you might be retrying on the same connection or a different connection, so there's more control on the user. But taking as a parameter, then there's also a much higher risk of someone starting to do the piping around of the interfaces. So it is a bit of a trade-off. In general, if you don't have a concrete problem with taking a longer lifetime, so for example, let's say your class, your dependencies allocate a ton of memory, right? You don't want to keep this ton of memory around for a long time if your memory constrained. It can make sense to evaluate passing as a function. Otherwise, in general, passing as a constructor is more intuitive. People are more familiar with it, and it's going to be simpler. But I think they're both valid solutions, and they can both work for the they're equivalent. At the end of the day, they're equivalent. So you just need to pick what makes more sense in your architecture.
It was first.
Yeah, exactly.
So when there was when you were trying to do the when you pass in the stood function, because you were saying that, you know, if you wanted the runtime, the open sets, right, that only has like a single behavior that you could expose. What do you think about the idea of passing in a custom type erased, you know, type so that you could encapsulate multiple behaviors but still maintain value semantics?
Okay, so you're basically saying instead of using an interface, an abstract-based class, when we have multiple behaviors, we could have a value type which provides multiple functions, basically a multifunction object which takes maybe 2, 3, or 4 functions. They're equivalent conceptually, so it's the same. I mentioned in the code to use std function, which is value type, because this is the type which is available for most people. It's been around for a long time. People are familiar with that. But in general, what I was saying initially is to take things as references. So in general, I would suggest to use function ref, because again, you don't need to force, for example, the copy. So if you wanted here, we would have used the move only function, but then we are still forcing to move in, right? We don't need to have the ownership. We can just use a function ref. But besides that, so for example, if you had a multi-function ref object, it's fine. It's a same. The goal here is that you need to have an explicit dependency with a clear contract, which you can control from outside what is the concrete behavior that's going to happen. As long as you can do that, you can use interfaces, you can use type arrays, you can use your custom type. It doesn't matter. These are just a bunch of options that in general are widely available and so are applicable. But definitely you can do that.
Are allocators just another form of dependency, specifically polymorphic allocators, or there's something special about them? The reason I'm also asking that is that there was some work being done for a proposals for language-level allocators. I was wondering what are your thoughts on that, and if it could be expanded to a general language-based DI proposal.
That is an interesting question. I knew there was a proposal for automatically propagating allocators. I don't think I ever read it. Or if I read it, it was a while ago, and I'm not up to speed. Is there a space for a language level support for dependency injection? Maybe. I honestly don't see too much what will be this functionality.
Let's say, for example, you have a dependency and you end up propagating this dependency not just to a single component, but also to sub-components of these components. You would have to do that wiring manually. Think about allocators, for example. The language feature will basically kind of like detect what dependency something needs, and if the parent has it, it would propagate it down at the same time. So do you feel like that happens with normal dependencies, or is it mostly specific to allocators?
Okay, so first, I want to clarify that one thing. The specific case of you take a dependency and you're propagating everywhere, you're piping. So if the case of allocators is valid because basically everywhere you're using memory. So likely at every step of this piping, you're also using the allocator. Piping is fine if you're accessing the data. If you're just propagating down, that's a problem. And I didn't get a slide because time was a bit limited. But if you follow these, you're never going to do piping. And the reason is you always have a control about, let's say, so basically at the top level, you have this allocator that you need to pass to a bottom layer, and you have in the middle a lot of components. If you look at how you're instantiating this component with dependency injection, the dependency is actually inverted. At the top, you have the most low-level component, and as you go down, there are higher-level component. So in your stack, you can pass this component to the lower level, and during dependency injection, everything else is not going to know about this dependency. Without a picture, it's a bit harder to explain, but if you try and create a stack of components and you instantiate them, you'll see that this is reverse. And that's why you never want to do piping, because there's always the alternative of passing the data directly to the component that needs it. So I hope this answers the question. Yeah?
So you said you recommend references, but when you pass a reference into a function or a class, you're explicitly telling the compiler that this could be accessed from somewhere else. Would it not be better to, in the case where you can offer that restriction, to always take it by value?
Yes, definitely. That's what I was saying with the immutable ref, which will basically give the same guarantee. With what I mean with immutable ref is something which basically forbids anyone from modifying the data underneath. So if you can take by value, it's a better const ref in the end. So definitely do. But in general, you're going to be, when you're taking by value, you're going to be careful about, is the type copyable? Is the size big? Is there a performance implication? So there's a bunch of evaluation to do, which is perfectly valid to do and take as value. But using the const ref, or ideally this immutable ref, is the most generic, the more generic thing. But definitely, when you can, use by value.
You did recommend using function ref. Have you found that it's more likely that the avoiding the requirement of copying that is better and less than that the compiler would elide that copy?
The reason to function ref, so normally if you take a function by value and you're instantiating directly through the Lambda, it typically works. The problem starts to happen if you're capturing inside the Lambda something which is move only. So if you're capturing a pointer. And then in the case, for example, using the move only function works. But starting from the idea that if you handle your follow structured programming and structured concurrency, your references are always valid, then why do you want to start making the copy or forcing like sometimes the indirection to go around having this unique pointer when you can just take the function ref, which is going to work for any of these things and just work. Basically, a bit the point of using references is that if you're structuring your program correctly, and with correctly I mean the lifetimes are always bounded to your scope, using reference is never going to be a problem. You're not like in a few years that I've been using these, we didn't have a dangling reference problem or a null pointer the reference because it's common in the code base in which I work that you follow structural concurrency and structural programming. So you're just not, you never take things and straight away. So since you have the reference which is available, at the end the function is going to still doing an indirection because of type erasure. So it's quite similar.
Thank you.
Welcome. Well, I think we are at time, so thank you very much.